Alright, welcome to the second part of this AP Physics C Mechanics Semester 1 final review. So we're going to just do some question preparation here. I've got a few MCQ for you and a full-length FRQ, all from the 2012 AP Physics C Mechanics exam, which was released by AP or College Board. So let's get right into it. So remember from concepts from the content review, I'll just review them as I do these problems. So I try to get a bunch of variety of problems so we can apply all the concepts we learn. Let's start with this one here. So this one's a circular motion problem, basically saying if you have a string that can hold a 10 kilogram mass, well, what force can it hold? That's going to be, I'm going to use G as 10 here. That's going to be Fg is equal to 10 times 10 or 100 newtons. And so that is basically the maximum tension force of the string. Now, if you spin it around in a horizontal circle, that means the centripetal force, which is going to be the tension force in this case, would also be 100 newtons. And now we can use the formula Fc is equal to mv squared over r. We get 100 is equal to m, it says 0.5. V is what we want to find. And over r is 2 meters long. And so you multiply both sides by 2, you're going to get 200 is equal to 0.5 v squared. So 400 is equal to v squared, which means v is equal to 20. And so your answer would be D, 20 meters per second. The second one here is a nice problem and talks about a lot of different stuff. So let's get right into it. So you got a ramp. Once you hit the bottom of the ramp, you're going to have a surface with friction, and you want to find out how long it slides. So let's come up with a plan for this. To find out how long it slides, we can use kinematic equations. We just need to know the acceleration, which we can get from forces. The friction force is the only force in that direction, and so you can find the acceleration from there. Now, to get the friction force, we can always get the friction force. It's just in the kinematic equations, we need the acceleration and also the initial velocity. What velocity would the block be traveling at when it reaches this point? Well, how can you figure that out? You can use work energy power. You could also do other ways, I'm pretty sure, but work energy power is probably the easiest. You have potential energy up here, you have kinetic energy down here. You just set them equal to each other. So let's get started. Potential energy initial, technically plus kinetic energy initial is equal to potential energy final plus kinetic energy final. But this initial is 0, this final is 0, because it starts at rest and ends at ground level. And so that just means UGI is equal to KF. UGI's MGH is equal to 1/2 mv squared. Now you might be thinking, we don't know mass. Well, the masses cancel out, luckily. And we just want to solve for v. So you multiply both sides by 2, so 2gh is equal to v squared, or v is equal to square root of 2gh. That means you can just plug it in. I'm going to plug in 10 for g, and it says 5 for h, so 2 times 10 times 5 is 100, so that means v is equal to 10 meters per second. Very nice numbers here. We don't even need a calculator. For the forces part of it, we can draw a free body diagram. We don't really need to, but Fg down here, Fn cancel each other out, Ff here. And that means Ff is equal to mu times Fn. I'm not writing any subscripts. It is k because it is moving, but they didn't give us any subscripts. So mu k times Fn. We do need to find the Fn there, but we don't know the mass because Fn should be equal to Fg. Fg's mg. We don't know the mass. What I always say in questions like these, if you find a variable that you're not given, keep it as a variable. It's probably going to cancel out sometime later in the equation, unless you just did it horribly wrong. But that's usually never the case. That means this is equal to mg, and so the friction force is equal to mu k times mg. Let's not plug in stuff yet. Let's keep it like this. Or actually, we can plug in mu k and g because we do know that. Mu k, it says, is 0.2, g is 10, so that's just going to be equal to 2m. That's the friction force. And we know force is equal to mass times acceleration, so 2m is equal to ma. Well, that's nice. The masses cancel out, and so a is equal to 2. Now, a little caveat here, it is actually -2, because friction is going in the opposite direction of the velocity. So yeah, we just need to be cognizant and be aware of the fact that acceleration would be opposing velocity. Okay, now that we have acceleration and initial velocity, we can do the kinematic equation. V final squared is equal to V initial squared plus 2a delta x. Because it has everything we need and we don't care about time. So v final is 0 because it ends at rest. This is 100 because 10 squared minus 4 delta x. And so you can just solve for delta x. It's just simple algebra here. It's going to be 24 0.5 meters. And so your answer would be E for this one. I really like this question for a few things. One, like I said, it combines a lot of topics, work, energy, power, forces, kinematics. Second, it gave us a way to like plan out a question for an MCQ. If you see all this, you should, in your mind, if you have the time, of course, like plan out what your steps are going to be. First, we're going to do work, energy, power to find the velocity. Then we're going to do forces to find the acceleration. Then we're going to put it all together with kinematics and find the displacement. And third reason that it had that example like where there was a variable we weren't given, but it cancels out later. So never panic when you don't know something. It's probably going to cancel out. All right, moving on here. This is a spring question. So, and we're given a graph. So it's a pretty nice question there. So the equilibrium position looks like this right here, 0.25. And it's pulled down to 0.35 at the start and goes all the way back up to 0.15 at its peak. It's asking for what time is the vertical velocity the greatest. Now, I did mention this in my content review where when the position is a minimum, the velocity is a maximum. There are small caveats to that because it wants the absolute value of the position and velocity. Because it considers like the extremes to be maximum position. Technically, you would say minimum position here, maximum here, but not according to like these equations, because you can always just switch the sign or whatever. These both are maximum positions. And you can think about it in a spring too. If you compress it, it's going to be a maximum position. If you expand it, it's also going to be a maximum position. So those both are maximum, and minimum is at the equilibrium because technically that's a position of 0. Now, that means that the minimum position would be equilibrium position. So the maximum velocity would also be equilibrium position. So let's see, let me clear some of this a little. So it can either be here or here. And let's look at the answer choices. 0 is definitely not right. 0.2, that looks like 0.2, so let's keep that. 0.5, definitely not right. 0.75, well, this does look like 0.75. And 1, definitely not that. So it's either B or D. Why do we have two possible answers? And that's because, like I said, absolute value of position and absolute value of velocity. They want the greatest velocity. That means the greatest positive velocity. One of these is positive, one of these is negative. Since this is moving upwards and this is moving downwards, the first one's going to be positive, the second one's negative. And so your answer would be B for this one, because that's the greatest positive velocity. Velocity does have direction. And so the greatest negative velocity would actually be the minimum value of velocity. So yeah, interesting question there. This one is related. It's asking for the spring constant. Well, we can just use that equation we got from the content review where omega is equal to the square root of k over m. So that you can derive if you don't memorize. I would suggest memorizing it. You don't have to if you don't want to, but I would definitely like know how to use that. Okay, so you plug in well, you can solve for k. K is equal to omega squared times m because you just square both sides and multiply by m. Omega, we can find out by finding the period. The period here is 1 second. For one entire cycle, it takes 1 second, which is pretty nice. So t equals 1, so frequency is also equal to 1 because that's just 1 over 1. And so omega is equal to 2 pi times that, which is 2 pi. Very nice. So this is going to be 2 pi squared times mass. Mass, it says, is 0.4, and so we solve for k. This is ugly numbers. We might want to use a calculator, but your answer is going to end up being 17, which is, A, which is 16 Newton meters. It's going to be around 15.8, but yeah. All right. All right, moving on to number 18 here. So this is more conceptual. Identical net forces act on the same length of time for two different spherical masses, which is the following describes the change in linear momentum of the smaller mass compared to larger mass. So we have a smaller mass, a larger mass, same force, same time. What is the change in linear momentum? Well, that's just change in P, which we know is J from the impulse momentum theorem. What else is J, impulse? It's equal to the force times the change in time. Hold on a second. If the forces are the same and the times are the same, then the impulse should be the same for both, which means that the change in momentum should be the same. That's weird. Why does it not depend on the mass? Well, it's just that the quantities cancel out. This is mass independent right here. Momentum might be mass dependent, but the impulse is really not in this case. And so your answer is going to be C. It's going to be equal to the change in linear momentum of the larger mass because they both are going to be the same. Okay, 21. Differential equations. You might remember from calculus, you might not. But what it basically says is you want an equation where it has the variable and its derivative in there. So it's Newton's second law, which is F equals ma, if you remember that, for simple harmonic oscillator of mass m and restoring force constant k. Okay, we do know that the force of a spring system is negative k delta x. And so that's going to be equal to ma. We can just rewrite this as negative kx because that's what the formats look like. Remember the negative sign, that's important. Positive is when you're dealing with energy, negative is when you're dealing with force and work. Acceleration, we want to write that in terms of x or derivatives of x. And so acceleration is just the change in velocity over change in time, derivative of velocity, and velocity is the derivative of position. So this m times d squared x over dt squared. And so your answer is going to be negative kx equals md squared x over dt squared, which looks like answer choice B here. So yeah, a little bit of calculus, mostly just math on this question. So you got to know your math for physics. I guess you didn't need to know like spring force and all that. All right, this one's a long one. 3 questions, both all based on this. So this is gravitation. You got positions 1 and 2. 1 is farthest away, 2 is closest, and this is 10 times as much as this. This means that it's going to be going faster here because of the higher acceleration. It's closer to the sun. This it's going to go slower here. It's asking at position 2, the kinetic energy is what? Well, it's going to be greater than 1. We know that. It doesn't look like there's an option like that, but it does say at the maximum value for the orbit. That is true. It's the closest, which means most acceleration, and so it's going to be going the fastest there. So that's going to be your answer for 22. 23, what's the ratio of speeds? Well, there's a few ways we can do that. I'm going to use the circular motion in quotation marks formula, which is just that the Fg is equal to Fc, which is equal to mv squared over r. Which means the formula for gravitational force is gmm. So I'm going to just use capital M for the sun and lowercase m for the comet over r squared is equal to mv squared over r. The m's cancel nicely. One of the r's cancels with the other, and you're left with gm over r is equal to v squared. And so v is equal to the square root of gm over r. All right. And that means that it's related to the square root of radius. And so you're going to be left with 1 over 10 if you use process of elimination. You know it's going to be smaller, and you know it's not going to be, that's squared. It's going to be smaller, we know that. And so it's going to be 1 over 10 as your answer. And then for 24, it's ratio of forces. We can kind of use the same logic here, but just with the forces. We don't have to deal with the velocity, right? And so this is based on the square of the radius, and so it's going to be 1 over 100. The radius was 10, so the square of the radius is 100. And so the ratio of the forces would be 1 to 100. All right. Last few questions here. All right. Block of mass m is pulled along the rough surface like this. We want to find expression for the magnitude of the frictional force. So let's draw a free body diagram here. We have Fg and we have Fn, which is not going to be equal to Fg. And the reason why is because of this force exerted on here. And then we have frictional force here. It is being pulled along, so it's going to be kinetic friction. All right. Let's break this force down into its components. We have vertical and horizontal. This vertical plus the Fn is going to be equal to Fg. So F, and the vertical is going to be sine phi. Because if this is phi right here, it's going to be opposite to that. So sine phi, not 5, plus Fn is equal to Fg. And so you can rewrite this as Fn is equal to mg minus F sine phi. Why do we need that? Because of the equation for kinetic friction force, which is mu k times Fn. So it's just going to be mu k times mg minus F sine phi. And so that's going to be answer choice E here. Again, a lot of math and manipulation, but still some physics concepts you should know. This next one here is momentum. You got a collision. So you can write m1i plus m1i v1i plus m2i v2i is equal to, and this one, they're going to stick together. So it's just, I'm going to call it m final, v final. They're going to stick together and be one object. All right, so let's solve for this. I think we have enough information. This is 1,500 kilograms. This is 4 meters per second to the right. This is 3,000 kilograms. This is -3 because it's to the left. And so 1500 times 4 is 6000, minus 3000 times 3 is 9000. And the total mass is going to be 1500 plus 3000, which is 4500. So it's going to be equal to 4500 times V final. So negative 3000 is going to be equal to 4500 times V final. And so V final is equal to negative 2/3 meters per second. Now it does ask for the speed, not the velocity. And so the sign doesn't matter. It doesn't have a direction. And so your answer is going to be 2/3 meters per second. All right. I think these are the last, this is the last question. Or no, sorry, we do have one more after that. So this one, ball 1 is dropped from rest at the time t equals 0 from a tower of height h. Ball 2 is launched upwards. So let's write different equations for 1 and 2. Let's say they meet at some point, which is delta x, or delta y, actually, from the position of ball 1. And that means ball 1 travels delta y. It starts with no initial velocity, so it's just equal to negative 1/2 g delta t squared. On the other hand, ball 2 starts at 0. It travels a total of h minus delta y, not just delta y, but h minus delta y, and that's equal to, this time it does have an initial velocity v naught delta t minus 1/2 g delta t squared. Now, if you were to add these two equations together, or sorry, one quick thing. This isn't technically right because delta y should be a negative value, and so this should be h plus delta y. A little caveat there, but if you were to add those equations, you would get something weird. In this case, you add you want h plus delta y, because if delta y is a negative value, then h plus delta y would be a smaller value than h itself, and so just pay attention to that. Now, I'm going to move this down here, and the reason why is because I want to subtract these two equations now instead of adding them. So if you subtract them, you're going to get h is equal to, these two also cancel out. So it's just h is equal to v naught delta t. And so it's asking for what time. So delta t is equal to h over v naught. And so your answer for this should just be c. Very simple. No like extra coefficient necessary. All right. Last problem here. Ball of mass m falls vertically, hits the floor with speed vi, rebounds with speed vf, magnitude of impulse. We know impulse is equal to change in momentum, which is equal to mass times change in velocity, because mass doesn't change, usually. V final minus v initial. Now, that looks like answer choice B. Very simple. Not that simple, because it falls down with the speed of vi, which means its velocity would be negative vi, and it rebounds with the speed of positive vf, velocity of positive vf. And so this just becomes vf minus negative vi, so vf plus vi times m. And so it's actually a trick question. That's why I wanted to include it. Don't just jump to the first answer that makes sense. Actually think about the physics behind it. Since it's at speed vi, you're going to want to do vf plus vi as your answer. All right. That was it for the multiple choice. Very quickly, we're going to do the free response question. This is a simple harmonic motion, specifically springs. It gives us this diagram and this graph. It's asking for an equation for v of t. We can easily do that because we do know how to write an equation for v of t. V of t, we know, is equal to technically it should be omega a times the cosine of omega t plus phi. Now, don't blindly write that because let's make sure that actually makes sense. In this case, it starts at 0 and then goes immediately negative. If it starts at 0, if it starts at the equilibrium position, then it should actually be sine, not cosine. The only thing that actually makes sense in those formulas that I showed you in the content review is the WA in the front. Not the actual sine or cosine, that depends on what the function is. Also, it doesn't start at a certain phase angle, it starts at 0, and so it's just omega t. Another thing is that since it immediately goes negative instead of positive, like a usual sign would be, this should be negative. Negative omega a sine omega t. One last thing, we don't know omega or a, because a is the maximum position. We're only given velocity, and so we can just write this as negative v max, because that is technically a valid sinusoidal function. It should be the negative amplitude of the function you're given, so that's negative v max sine omega t. What is v max? Well, what does that look like? If you, on the actual exam, you would have like a pencil that you can actually check through. This is a pretty thick pen, and so I know that the answer is negative 0.16, but you would estimate it on the actual exam. And then it's times the sine. What's omega? Well, we can do the same thing we did for that multiple choice problem, find the period. This is going to be a bit more difficult because you start here, you want to end here. What is that? That's 0.7. You have to do 1 over 0.7 to get the frequency and multiply that by 2 pi to get the angular frequency. That's going to be 9 if you calculate it. So it's going to be 9t. And so your equation for v of t is going to be negative 0.16 times sine of 9t. And you would, I guess you don't need units for AP Physics, but it would be you don't need sig figs for AP Physics, but it would be 9.0t. For the second one, it says find an equation for x of t. You can just integrate this. Now, one thing about this is u substitution. So you want to write sine of u times du, but we also know that du is equal to 9 dt because u is 9t. So if you took calculus, you would know that you would just need to multiply this by 1/9 because of u substitution. You can also take out this negative 0.16, and you're going to get negative 0.018 times the integral of sine u du. Integral of sine is negative cosine, and so the negatives cancel nicely. It's 0.018 times the cosine of u. U we said was 9t, so it's going to be 9t. And then technically plus c, but it says it starts at x equals 0, and so we don't need a plus c. That's going to be our equation for position. And finally, calculate the value of k. Remember that equation, omega is equal to square root of k over m. Well, we know omega was 9. We know m is 0.3, it says. And so we square both sides. 81 times 0.3, you're going to get a k of 24. And the units is newtons per meter for this, because force is equal to negative k delta x. So this is newtons, this is meter, and so that should be newtons per meter. All right, not bad. Final 2 questions. It's a different experiment this time, not the exact same one. So this time there is a mass here and a distance d there. It's saying when it's compressed at distance d and the block is moving towards equilibrium position, so it's like right there and it's moving this way. What are the forces going to be? So obviously there's going to be gravitational force downwards and normal force upwards. Those don't change, they're equal to each other. And I'm also going to draw that for this too because it's the same for both of them. What is going to change is like the restoring force and the so the restoring force is just the spring force, and then there's also friction, because it is a rough surface. So the restoring force is always going to be the opposite direction as the position. Like I said before, because acceleration is equal to negative omega squared times the position. So force is equal to negative m omega squared times the position. So it's always that negative sign before the position, which means that if the position is to the left of the equilibrium position, that means your force would be acting to the right. And so no matter what, even if you're moving away or towards the equilibrium position, your restoring force, your spring force is going to be to the right. What does change is the friction. Since you're moving towards equilibrium here, friction is going to be the opposite way here, not as much, so FFK, not as big as FS. If you're moving away from the equilibrium position, it's going to be actually along with your spring force, FFK, this way, because it's always, it's usually opposite direction of motion. I'll keep that. And then finally, draw a sketch of V of t. I cannot draw a very great sketch on here, but there's 3 main things you need to hit. One is like the period of it, basically. It needs to still have a period of 0.7. And so let's start here. And 0.7 is right here. So it needs to go through equilibrium again here. And so it also has to go through it at 0.35. Because, well, it goes up one way, down, up. That's one entire period. So it needs to go through all 3 of these. And then it has to be, it has started 0 and started increasing positive velocity because it starts moving to the right. And then finally, it has to be what's called damping. Basically, since there's friction, the velocity is going to decrease over time. So it's not going to be perfect sinusoidal. In fact, it's going to... Okay, let's try this again. It's going to be something like this. Maybe not go all the way to 0, but definitely show decreasing over time. So that should get you credit for this question. All right, and that's it for this video. I know it was shorter than the previous video, but basically I focused more on the content review for this. So that's it for AP Physics Semester 1 review, and as always, good luck on your finals, and if you're going to use this video for your actual AP exam, good luck on your AP exam as well. And yeah, let us know how you did. Hopefully you found this helpful, and I'll see you in second semester with both rotation and then electricity and magnetism. So see you then, good luck.